Let's talk about trees. Tree is a graph in which there is exactly one path between every two vertices. If you maintain and if you remember this condition, then easily we can understand trees. So whenever I say tree from now onwards, you should remember this condition very strictly. That is, between every two vertices there is exactly one path. Okay, it's not less than that, it's not more than that. So we'll see some of the examples and we'll check whether they are trees or not. So consider this one: 1, 2, 3, 4, 5, 6, 7, 8. This is not a tree. Why? Between 2 to 8, the number of paths are 0. But between every two, there should be exactly one path. Hence, it is not tree. Let me add 2 to 8. Now, if you take any two vertices, I can show exactly one path. Between 1 to 8, there is exactly one path. Between 1 to 3, there is exactly one path. In that way, between every two vertices now, there is exactly one path. Okay, if I add one more edge like this is not tree. The reason, between 1 to 3, I can show you two paths. 1 to 2, 2 to 3. Second one, 1 to 4, 4 to 3. Correct or not? So there are two paths I can see. That's why this is not a tree. Okay. So from now onwards, you remember, whenever a graph contains cycle, what happens is like this. So this is what I am showing here, x, y. Then between x comma y, you will have two paths. You see, one path is like this, right? Then another path is like this. Just I am showing directions only to illustrate that there are two paths. Okay, so it doesn't mean that the graph is directed. So between x to y, you can see one path. Between y to x, there is another path. Whenever there are two paths between any two vertices, that graph cannot be a tree, right? So that's why this is not a tree. From now onwards, any graph contains cycle, that cannot be tree. Second one, tree cannot have disconnectedness. That means graph is disconnected, then that cannot be tree. The reason, again, it violates the formula, that it violates the definition that the number of paths between one component of vertex of one component to vertex of another component is 0, but it's supposed to be 1, right? So that's why disconnected graph, anything is not a tree. Let's try to prove this theorem. I read that theorem: a graph is tree if and only if it is connected and it does not contain cycle. So we are going to prove this theorem using the definition of tree. First, understand the structure of this theorem. It looks like P, this is, let's say, P, if and only if it is connected and does not contain cycle, entire thing is Q. In proposition logic, I taught you P if and only if Q is nothing but P double implies Q. So that is nothing but P implies Q and Q implies P. So proving this theorem is nothing but proving that P implies Q true and Q implies P true. Let's focus on P implies Q. How to prove that P implies Q true? That means we have to prove that P implies Q tautology. Whenever P implies Q tautology, whenever P is true, we assume P equal to true and we prove that Q equal to true. Okay. Now similarly, to prove that Q implies P is true, whenever Q is true, we have to prove that P is true. Why so? The reason, when Q true, P false, this is the only place Q implies P will become false, then overall formula, which is a theorem, which will become false. Understand? So that's why, in simple words, so if you study proposition logic, you will understand it clearly. That's why before coming to this video, please go through proposition logic and tautology topic. Okay. So to prove this kind of formula, whenever P is true, Q should be true. Whenever Q is true, P should be true. First, let me take P implies Q component. Okay. So I prove that P implies Q. What is P implies Q is, here P is graph is tree. Okay. So I am writing it. If graph is tree implies, then it is connected. That means graph is connected and contains cycle. Does not contain cycle. Okay. So I prove this one. For that, the model already I taught you that left is true and we prove that right is true. Assume left is true. Then for that we should take that your graph is tree. Remember, your graph is tree. If your graph is tree, what is a tree definition? Between every two vertices there is exactly one path. Remember it in your brain. Now I draw the structure. We have a graph. It is a tree. That means between every two vertices there is exactly one path. Now we have to prove that it is connected and it does not contain cycle. Whenever I do that, then one direction of proof will be done. Okay. So for that, graph should be connected. Let's say we are wrong. This is called proof by contradiction. First we assume that this entire thing is false. Okay. Maybe graph is not connected or graph has cycle. See here. If this is false, then either graph is disconnected, otherwise graph contains cycle. Let's take case number 1. Graph is disconnected. Whenever graph is disconnected, already I told you that cannot be tree. But already we assume that graph is tree, then graph cannot be disconnected. So this definitely graph should be connected. Then what is the other thing might be false? Does not contain cycle may be false. If does not contain cycle is false, then graph should contain cycle. If graph contains cycle, already I told you that there will be two paths between any two vertices, right? At least two vertices. Example, x and y are the two vertices, on between them let's say there is a cycle, then you can see two paths. But that is not possible in a tree. Then so graph does not contain cycle should be true and graph is connected true. So what I proved is whenever I am taking graph as tree, so connected is becoming true and does not contain cycle is becoming true. That's why this direction is correct. So that means whenever graph is a tree, definitely it does not contain cycle, it is connected. But be careful. There is another direction. I did not prove about other direction. What is that? We'll see. Q implies P. Let's see that Q implies P. So Q implies P is like this. If some graph is connected, reverse, right to left. So graph is connected and does not contain cycle, does not have cycle, then we have to prove that P. What is P? Graph is tree, G is tree. Why? How to prove this kind of statements? For that we assume first left is true and we prove that right is true. Let's assume left is true. For that this should be true. Q means this one, right? Graph is connected and let's say graph does not have cycle. So imagine a structure which is a graph, okay, and assume these two things. Graph is connected and no cycle. Then why it should be tree? Why it should be tree? So again I use a method of proof called proof by contradiction. First I contradict myself. That means I assume initially that this is false. What is that? P. Okay, let's try this combination. Left is true, right is false. If you can do it, then you are violating the theorem. Then theorem will become wrong. Let's try that. For that, G is tree should be false. Then graph should not be tree. If graph is not tree, there are two cases. Why? First go to the definition of tree. Tree is a graph is a tree. Tree is a graph, sorry. Tree is a graph where between every two vertices there is exactly one path. Let's say that is false. Let's say G is not a tree. Okay, I am assuming that P is false. That means graph is not a tree. Then two cases will arise. First one, why something is not tree? Maybe there is, between two vertices, there is not exactly one path. If between every two vertices there is exactly one path, it is a tree. Probably there are two vertices x comma y. Okay, between these two maybe there are zero paths. That's why it is not tree. That's one case. But already graph is connected, then it is impossible. Then try to violate this P as false. Graph is not tree. The second reason is maybe between two vertices there are multiple paths. Then it forms cycle, isn't it? Whenever between two vertices if you see multiple paths, it forms a cycle, but graph does not contain cycle. So you can't have multiple paths between two vertices. You can't have zero paths. Then definitely the other case is you should have exactly one path. That is what P says, right? What is P? graph is a tree. That's why your graph definitely should be tree. I tried to make G as non-tree, but whenever I made G as non-tree, either I am violating connectedness, otherwise does not have a cycle. So we are violating these two things. But already given that G is connected and G does not have cycle, then always you are ending up with tree only, right? So that's why I proved Q implies P. Okay. So finally the summary, we proved P implies Q and Q implies P. Whenever P implies Q, Q implies P are proved, then we proved P double implies Q. That means P double imply P if and only if Q is proved. Understand? So here if and only if is nothing but double implication. So in that way we proved this theorem. Let's see two more theorems about trees. In a non-trivial tree there exists at least one vertex of degree 1. So what is non-trivial tree? It's a tree with at least two vertices. So this is called trivial tree if there is only one vertex. So when there is only one vertex, then this is a tree, because between every two vertices there is exactly one path. So example, here it is x, then x to x there is a trivial path. You know what is trivial path, already I taught you in connectivity. So from x to x there is one path, so that's why it is a trivial tree. Now what is non-trivial tree is, it's a tree with two vertices, at least two vertices like this, x comma y. So this is a non-trivial tree. Now similarly x to y, maybe y to z, a, this is a non-trivial tree. So at least two vertices should be there. And in such trees, what is this theorem says that there exists at least one vertex of degree 1. We'll see what is the reason. So I'm going to do the proof. Okay. First of all, we assume that this statement is wrong. If this statement is wrong, then what happens? There should not be at least one vertex of degree 1. Then every vertex degree should be either 0 or more than 1, isn't it? But degree 0 is impossible. The reason, if you have a degree 0 vertex, then graph definitely will be disconnected, right? So that's why degree 0 is not allowed. Then only possibility greater than 1. So every vertex degree greater than 1, then at least you should have two edges to it, correct or not? Let's take one vertex in that graph. Okay, this is your tree or graph, but you know it is given that it's a tree. Let's assume it is a tree, and in tree, if every vertex degree greater than 1, then every vertex should have at least two edges like this. Okay, let's assume that the first vertex is v1, any random vertex, let's call as first vertex. Then this v1 is associated with at least two vertices, right? Maybe v2 and v3. So I'm going to use the technique called morning walk. I imagine v1 as a point. From v1 point I will go to v2. So using a walk. Okay, since we have an edge, we know that there is an edge, I can go like this. Then once I come to v2, just I say that I just entered v2. It's a new vertex. Then just I have taken one edge of v2, then still there should be one more edge, y. Whenever I ask a y question, stop the video and think about it until you get the answer. Okay, once you get the answer, continue the video. Now since every vertex degree greater than 1, otherwise greater than or equal to 2, then this v2 should have one more edge at least. It can have some more edges, but at least one edge should be there. So let's say that is this one. Now that is going to a vertex called, let's say, v4. Okay, then again same things. I'm doing morning walk, right? I started at v1, I will go to v2. Since it has one more edge, I will go to v4. Then v4's degree also at least 2. Then I just entered v4. Then there should be one exit. Then I will take it. Then I will go to v5. In that way, I will do this morning walk. After some time, what happens? I should repeat the vertex, which is part of this graph. Why I should repeat the vertex? If I don't repeat the vertex, then my vertices will be exhausted. Okay, let's say case number 1. If I am repeating the vertices, what happens? Example, if I go back to v2, then what happens? See this one, v1 to v2, v2 to v4, v4 to v5. After that, if v2 comes, then it forms a cycle. But tree does not contain cycle. Then you never repeat the vertices in this morning walk. So you cannot repeat the vertices since it's a tree. Then what to do? Then you should take every time a new vertex. Let me take a new vertex every time. Okay. So why are you continuing like this? Why you are capable of continuing that? The reason, every vertex degree 2, if whenever you entered into that vertex, definitely there should be exit. So that's the logic to say that we never stop. But we should stop. Why? This graph is finite graph. If there are 100 vertices, now if you do this morning walk after 100 times, you will cover all the 100 vertices, right? Then after that you will not see any new vertex. Then you should repeat the vertices. But if you repeat the vertices, there will be a cycle. Then you should stop, because this is, let's say, in the process last vertex. Correct? Because you can't go for infinite time. The reason, there are only finite vertices. Then after some time, definitely you will stop at some point. Let's say that vertex is V100. Then I will ask you this question. What is that is? Why are you stopping here? Your answer is, there is no other vertex to go. Then I will ask you, really there is one more edge to it. Then you can go to that point, right? Right? Then the only reason you are not going to new vertex is, definitely its degree is 1. You can't escape now. You can't say that I can go. If you can go, then you should go. But if you are going, then since you said you are not repeating the vertices, then definitely you should go to a new vertex called V101. But this process you can't do forever. The reason, there are only finite vertices. Example, if you have 1000 vertices, after 1000 times if you do, then you end up with a situation where you don't have extra vertex to continue. Then I will ask same question, why are you stopping? Then you should agree that this is a degree 1 vertex. You can't escape. That's why. So this morning walk can prove that there exists at least one vertex of degree 1. Understand? Let's see one more theorem. In a non-trivial tree, why there exist at least 2 vertices of degree 1? Already we proved that there exists at least one vertex of degree 1. But why there exist at least 2 vertices of degree 1? Okay. Previous statement is correct, but this is also correct. Okay. So why, we'll see. Since already we know that in a tree, because it is non-trivial tree, definitely there exist at least 2 vertices. Okay. Let's say one vertex is u. And I assume that, let's say, degree of u is 1. Okay. We know that. Degree of u1, because there exists at least one vertex of degree 1. Start here, do the morning walk. Since it has at least one edge corresponding to u, then it will reach you to v1. Then same story. If v1's degree is 1, then there will be 2 vertices of degree 1. But let's say theorem is wrong, then its degree should be 2 at least. Then you will see an exit for v1. If there is exit, it will go to another vertex v3. Then whenever you enter into that v3, there should be one more exit. Why? Because its degree also should be 2. If at any time, if a vertex degree is 1, like example v5's degree 1, then this one and this one will become 2 degree 1 vertices. But to deny that, you should continue going. But whenever you go like this continuously, since the number of vertices in your graph is finite, you have to stop somewhere, otherwise we should repeat the vertices. If you repeat the vertices, graph contains cycle, but your graph is tree, that is impossible. You can't repeat the vertices. Then whenever you don't repeat the vertices, after some time, all your vertices will be exhausted and we should stop somewhere. Whenever you stop, then I say that, so I just entered this vertex, but I cannot, I am not able to go out. The only reason for that is definitely it's degree 1. If really it has one more edge, I would have gone out from this point. But why I am not able to go? The only reason is it's degree 1. Correct? But why don't you go? If you go like this, then your vertices will be exhausted. You have only finite vertices. At some point of time, you will run out of the vertices and you will stop somewhere. Okay, because all your vertices will be gone. Then this is the last vertex in your total graph. Let's say V100. I assume that there are 100 vertices. Then all vertices you have visited and you reached this point. Then there is no extra vertex to visit. Then if you can't repeat the vertices because it forms cycle, then you have to stop. You are stopping here means its degree definitely should be 1. Understand? So in that way always we can prove that there exist at least two vertices of degree 1. Okay, I'm going to prove this thing. I'm going to prove this thing with mathematical induction. So generally most of the students, afraid of mathematical induction, but it's a very easy concept if you understand it clearly. Okay, so first I will give you the idea about mathematical induction. In mathematical induction, step number 1 is we prove the statement for base case. So what I will tell you what is base case. So base case is nothing but generally a case where n value is very small. Example, whenever I say I am proving this statement with mathematical induction, then I have to take one variable. Okay, so let me prove this statement using number of vertices. Okay, so I am applying mathematical induction on number of vertices. Whenever I apply mathematical induction on number of vertices, then base case will become small, n value 1, otherwise n value 2. That means we have to take very small tree with respect to vertices. So when n value 1, this is smallest tree, right? So this single vertex. So this single vertex is a trivial tree, of course you know that. Then the number of edges in it. So why it is a tree? Anybody has question? Then you see. So here in this graph, already we know that single vertex is connected, right? Second one, any connected tree without cycles is a tree, right? That's why it's a connected tree, connected graph, and no cycles. That's why definitely it should be tree. Now in this tree, number of edges, let's count 0, which is n minus 1. Absolutely right. Let's take two vertices and first form connected graph without cycles. This is a structure. Then in this number of edges are n value n2, then 1, right? That means number of edges equal to n minus 1. Perfect. So I proved it for base case. That means I covered base cases where n value 1, n value 2, but still a lot more to go. That means n value 3, n value 4, n value 5. So there are a lot of trees with n value 3, n value 4, n value 5 up to n value infinite, right? Almost, not exactly infinite, because we are only covering finite graphs. That means n value 3, 4, 5, so on. For every natural number we have to prove it. But how to do it? If you do list out, like take all the trees with 3 vertices and check it out, all the vertices with 4 vertices and check it out. Is it a good idea? Not a good idea. The reason, it takes infinite time. So how to reduce the time? That's why we use mathematical induction. In mathematical induction, step number 2 is, this is step number 1. In step number 2, we assume something. Okay, so what we assume is, we assume that every tree with n vertices has n minus 1 edges for smaller trees. Let's categorize smaller trees as something like n value, like number of vertices less than n. You see, we assume every tree with, let's say, less than n vertices, okay, less than n vertices has this property, has above property. That means what? It's like this. So let's say this is 1, this is 2, number of vertices 1, 2, 3, so on. This is point n, number of vertices here n, then so on. Okay, then we assume that for all the trees with up to n vertices, that means less than n vertices, will satisfy this property. Just assumption, I don't know whether it is correct or not. Okay, that means I want to assume that 3 vertex tree will have 2 edges, 2 vertex tree has 1 edge, in that way 5 vertex tree has 4 edges, so on up to n. Okay, but I don't know after this n, like for n vertex tree the number of edges I don't know, for n plus 1 vertex tree number of edges I don't know, then I prove for it. Okay, so if I do that, what happens we'll see later on. First let me do it. This is the generally procedure for mathematical induction. Let me complete it. After that I'll explain you whenever I do all these things why this theorem will be proved. I will tell you. First of all, let me assume that every tree with less than n vertices has that property. Okay, remember it. That's assumption. Now let me construct a big tree which is having, let's say, n vertices. Okay, let's take n vertex tree, and the number of edges in that n vertex tree We don't know, right? We assume every tree has this property only up to less than n vertices, but for exactly n vertex tree I don't know. Let me prove that. What I am going to do is I prove that this tree has n minus 1 edges. How? I'll show. Let me construct the tree first. Okay, there are some properties of this tree, that is every tree has at least one vertex of degree 1, isn't it? At least one vertex of degree 1, you know that, right? So already I proved it. So this is, let's say, your tree. So I am just representing it like a tree, but I don't know what is actual tree structure. This graph is a tree which is covering all possible trees with n vertices. This is a random tree. Okay, so I am not assuming any particular tree. Okay, so let me take a random tree, and that random tree, so we know that there is at least one vertex of degree 1, that is for sure. Apart from that I don't assume anything. Okay, let's call that vertex, let's say u. Now let's see the properties of this tree. In this tree, if this is a vertex, let's say one vertex, then there are n minus 1 other vertices, isn't it? Now what I do is, if I remove this vertex, then only this edge will be removed, right? Then the remaining structure is again a tree. Yes or no? Why the remaining structure is tree? Because so there is a path between every two vertices. If you remove an edge, which is and this vertex, then that will not disconnect the tree. Okay, that is not disturbing any other paths. Like example, here to here you can go, everywhere to everywhere. So this edge is only, connecting all the other vertices to this node, right? This node. If you remove this edge, that will not disconnect the tree, correct? Then in the remaining tree, how many edges, how many vertices will have? Definitely n minus 1. Now how many edges you will have? Because already I assumed that every tree with less than n vertices has above property. Then if that has above property, then number of edges is supposed to be n minus 2. Okay, so now this component has n minus 2 edges, remember it. Now go back to our original tree. What was our original tree? Our original tree is this component followed by one extra edge and one vertex u. Let's come back to our original tree. This original tree has n vertices, right? But how many edges this tree has, we don't know. But let me count it now. Already this component has how many edges? N minus 2 edges. Let's write it, n minus 2 plus how many edges this part has? 1. Then overall become n minus 1. So we proved that a tree with n vertices has n minus 1 edges. But some students say that, sir, you are cheating. Why? You assume that every tree with less than n vertices has this property. What if this is wrong? Then your entire story is wrong, isn't it? Yes. Whenever this is wrong, this entire story is wrong. Absolutely. But still, this theorem is proved. I will tell you the reason. Okay. So let's summarize whatever we did. Okay. So I'm summarizing here. First of all, we proved for base case, right? So base case means n value 1 or n value 2. For that we have validated the theorem, right? So this was correct. Now we know this statement as correct. That is, if n minus 1 vertex tree has this property, okay, has above property, then definitely we know that n vertex tree has above property, right? That is what we constructed finally. I took n vertex tree, and whenever n minus 1 vertex tree was having n minus 2 edges, then overall edges will become n minus 1. That means whenever a smaller tree is satisfying the property, bigger tree was satisfying the property. That is what I write here. See, if n minus 1 vertex tree has above property, then definitely n vertex tree has above property. That is what we proved. But your question is, why this should be true? Need not be, right? This may be false. Okay, but how I use this statement to prove for everything? So what is our final goal is, in simpler words, we have to prove that a tree with n value 1, n value 2, n value 3, every tree should have n minus 1 edges, right? Let's take n value 1. Since base case is correct, we know that, we validated it already, then I proved it. Okay, done. Let me mark it. I have to mark everything, right? Okay, let's take n value 2. Read the statement. Since this statement is correct, no doubt on that, right? You have a problem with this one, this component, but overall statement is correct. Then substitute n value 2. Then what happens? 2 minus 1, 1. If one vertex tree has above property, then I can construct a 2 vertex tree like this. Okay, then I can validate for 2 vertex tree. Let's read it with n value 2. 2 minus 1, 1. One vertex tree has above property. Yes, already it is there. Then assume that it is true. Now it is perfectly true for n value 2. Then n vertex tree, that means 2 vertex tree has above property. So definitely it should be true. Correct? Then it is proved for n value 2. Substitute n value 3 now. If I substitute n value 3, then you will understand clearly. 3 minus 1, 2. If 2 vertex tree has above property, just now we proved it. Of course, otherwise you can see here also, it's correct. Otherwise, just now we checked it. If two vertex tree has above property, then according to this, n value 3 I am taking, then 3 vertex tree also should have this property. Yes, then definitely 3 vertex tree has a property. Why? Already 2 vertex tree has a property. Now see, 3 vertex tree also has this property. Now n value 4 also we can, for n value 4 also we can prove. How? Substitute n value 4. If 3 vertex tree has above property, already we checked it. So for n value 3 it was correct. That's why for 4 vertex tree it should have. In that way, so just by substituting n values, then we can check that this statement covers every tree. Okay, so I can prove for n value 4, I can prove for n value 5 simply by substituting here, right? So whenever for 4 it is correct, for 5 it should be correct. Whenever it is correct for 5, it should be correct for 6. That is what this construction did. Understand? So finally, this is called mathematical induction. Okay, using mathematical induction, easily we can prove this kind of things. So remember 3 points. Step number 1, you should prove for base case. Second one, we have to assume for smaller problems like n minus 1 or n minus 2. Like, so here n is our variable. For all the variables up to n, that means all the values up to n or less than n, we should assume it as true generally. Then we have to target n and we have to prove for n. By assuming for smaller values property is correct, and you have to prove for exactly n value. If you can do it, then it covers every case. Understand? Let's prove one more statement. A connected graph with n vertices and n minus 1 edges is tree. Why? So this is one directional. That means we have to prove that any connected graph with n vertices and n minus 1 edges is definitely tree. Okay, so why it is true? Before that, these two things, I am going to use these two things. Just let's recall them. A tree with n vertices has exactly n minus 1 edges, right? So whenever you have a tree, it will have definitely n minus 1 edges. Now, a graph is tree if and only if it is connected and has no cycles. So whenever a graph is, it's a two directional. That means tree means connected and no cycles. And any graph which is connected and no cycles, definitely it is tree. Already we proved it, right? So remember these facts, and using that, so we prove this one. What is that? This statement says that a connected graph, let's take a structure just for imagination. You have a connected graph, remember it. Note down it. Connected graph with n vertices. Okay, let's assume that there are n vertices. Fine, not an issue. So take it, and one more thing, we have to prove that it is given that n minus 1 edges also included in that information. Okay, that means your graph is connected and it has n vertices and n minus 1 edges. Then why it should be tree? So don't get confused with this one. Which one? Previous result. What is that? A tree has n minus 1 edges. It doesn't mean that every graph with n minus 1 edges is a tree. So that we did not prove, right? We proved that every tree has n minus 1 edges. But you have now a structure which is connected graph, and it has n vertices and n minus 1 edges. But why it should be tree? That we did not prove up to now, right? We are going to prove it. So if you want to prove on your own, stop the video and start thinking. After some time, if you understand it, it's not required to follow this video. If you don't understand, come back and watch this remaining video. So how I do is, first of all, I always remember this information. I have connectedness and n vertices and n minus 1 edges. Now we have to prove that why it is a tree. Let's assume that, again always same technique, proof by contradiction. Let's assume that this is not a tree. Why something is not a tree? Something is not a tree, then definitely the tree will be. So what's the definition of tree? Tree is a structure which has, we know that a graph is tree if and only if it is connected and has no cycles. Already it is given that it is connected. Then why it is not tree? Really it is not a tree. This should happen. Has no cycle should become false, right? Then definitely, so maybe this graph has cycles, right? That means this graph. Okay, here there is a cycle. This is the only reason your graph, this is the only reason for your graph should be not tree, right? So you are following, right? I have taken connected graph and n vertices and n minus 1 edges. We have to prove that it is tree. For that I assumed initially it is not a tree. If really it is not a tree, then maybe graph is disconnected, but no, it is not possible because graph is already connected. Then only other reason is, see, a graph is tree if and only if it is connected and no cycles. Then if it is not a tree, definitely either this should be false or this should be false, but already connectedness is true, then graph should have cycle. If graph has a cycle, then what I do is, there will be two paths, right, like this, because it's not a tree. But whenever you have cycle, I can remove one edge from it, okay, then number of edges will become n minus 2. But graph will not be disconnected, yes or no? I am not disconnecting your graph, and initially you have G, then I converted that graph to G dash. By what? Removing one edge on cycle. If you have one more cycle somewhere, remove edges on that cycle and remove the cycle. Okay, but whenever you remove an edge on the cycle, that that will not disconnect the graph. Already we have studied it in connectedness, right? So that's why you form G double dash. In that way, remove every edge on cycles and remove all the cycles. Then you form a graph which is a final graph, let's say G final. What's the property of G final? G final is again a connected graph. Why? Since G is connected and you are only removing edges on cycles, then that will not disconnect the graph, we know that. Then finally you get a graph which is again connected, but definitely you removed at least one edge from it because there was one cycle, right? Then definitely you are forming a graph with fewer number of edges than n minus 1. Already given that in the problem there are n minus 1 edges. Maybe number of edges are, if you do one time, then number of edges will become n minus 2, maybe n minus 3, maybe n minus 4, so on, right? Finally the number of edges in G final graph is less than n minus 1, right? Then this is definitely tree. Why? This is connected graph and I removed all the cycles, then this graph doesn't have any cycles. Any connected graph without cycles supposed to be tree. That is the definition of tree. See, a graph is tree if and only if it is connected and no cycles. So I am using that result and I am saying that G final should be dash tree. But number of edges in this graph now less than n minus 1 because you removed some of them. After removal of some edges, then if you form a tree, then that tree should have less than n minus 1 edges. But no tree, already you know this one, every tree should have how many edges? N minus 1 edges. But you have less than n minus 1 edges. Then definitely you are wrong. So you got a tree with less than n minus 1 edges means definitely it is impossible. How did you get that impossible thing? Where did you start? So how you arrived to this point? From here. Initially you are here. Then after that this one. But this process is correct, right? So this process is not at all wrong. Removing a cycle on a graph, removing an edge on cycle definitely will not disconnect the graph. Then definitely you will have a connected graph everywhere. So this process is correct to arrive to tree. Then what's the mistake? Only mistake is your initial assumption. What is that? Your assumption was, so this connected graph with n vertices and n minus 1 edges is not a tree. You thought it's not a tree. That's why you assumed a cycle. Whenever there is a cycle, I can remove it and I can remove it. In that way, I can end up with a tree. But that tree will have less than n minus 1 edges. That is impossible. Then only possible is, your assumption is wrong, right? So that's why, what was your assumption? this is not a tree is wrong. Whenever it is not a tree, then I can do all this process and I can prove that there is a tree with less than n-1 edges, but which is impossible. Then we can't prove a thing which is impossible. Then we have to change our assumption. What is our assumption? Initially, that this structure is not a tree, then it is wrong. Then definitely that structure should be tree. Try to understand the way how I am doing the things. If you follow them, so initially it takes a lot of time for you to understand these things. If you understand them, then you are going in right way. I will tell you the reason. In interviews, example, once you done with your gate exam, let's say if you get 200 rank, 300 rank or 1000, then you get call letter for interviews for IITs, right? Then at that time they will see your this kind of understanding skills, like they give a problem, they ask you to prove. If you don't have enough proving skills, just if you have rank, then definitely they will reject you. That's why discrete maths is very important in that way. Okay, so that's why understand how to construct the things. Here I am constructing lot of things. Try to understand them. This is called constructive thinking. That is very important. Okay.